Okay, let's consider a nice Newton's second law problem. Let's say we've got a chest, and this chest has a mass of something like 100 kilograms. And we've got Bob here. And Bob is pushing this chest, and he knows that he's pushing with a force of, let's say, 20 newtons. So, Bob is pushing and pushing, and he's like, alright, this chest should be accelerating. In fact, it is accelerating. Bob is successfully pushing it. Moves along the floor. So let's take a look at what Bob thinks is going on here. We've got this chest. We know this chest has gravity acting on it. We know it has a normal force acting on it. And it has this push acting on it. And this is on the chest by Bob. So, Bob is thinking, alright, I'm a big, strong, burly man. I can move furniture. And he says, I know that if this is the direction I'm interested in, the horizontal direction, then from Newton's second law, I know that F net is equal to ma. And so Bob says F net in this case is his push. It's the only thing acting in that direction. So that should be the mass of the chest times its acceleration. So the acceleration of the chest should be his pushing force divided by the mass, which should look something like 20 newtons divided by 100 kilograms. Or, let's see, that would be 0.2 meters per second squared. So this is what Bob thinks should be going on. But Bob notices as he pushes it, he is in fact seeing an acceleration smaller than this. Actual acceleration of it, 0.1 meter per second squared. This is Bob thinking, what could possibly be going on here? He double checks the mass of the chest at great expense to himself and his lower back. Confirms the mass of the chest is in fact 100 kilograms. He double checks, he goes, let's not worry about how he does this, but he double checks his own strength and discovers he can in fact apply a force of 20 newtons. So he's got to figure something is wrong here. So, he thinks, alright, he's got the chest, he knows gravity is definitely doing its thing, he knows the ground is definitely flat, he knows he is definitely pushing. So he has to assume that there is some friction going on opposing his efforts. And so what happens now, when he goes and does Newton's second law, he looks at this, and instead of it being just the net force being his push, the net force is his push minus the friction force. And this minus sign is important, and it's because they're in opposite directions. Just like when we were doing, motion, and we said, you could go to the left, you could go to the right, you could be to the right, you could be to the left, you could be speeding up, you could be slowing down. That minus sign was telling us there's a difference of direction. So here we have a force to the right and a force to the left, so it's their difference that is the net force. And so this is going to be what's equal to ma. And so now he's saying, alright, how big is this friction force? Well, we have F push minus ma is equal to the friction force. This is still his 20 newtons. This is 100 kilograms times 0.1 meter per second squared, because that's the actual acceleration of the chest. And so this is 20 newtons minus 100 times 0.1 is 10 newtons. P.S. A newton is a kilogram meter per second squared, because a force is a mass times an acceleration. These brackets tend to mean units of, but whatever. Anyway, so the friction force, 10 newtons. Turns out friction half as strong as Bob. So this is a nice example of a Newton's second law problem. The goal is to translate this free body diagram into an equation so that we can do some math and figure out quantitatively what's going on. Hopefully this helps as an example as you start doing the homework. Let me know if you have questions.